Welcome to the deep dive. Today we're going to be kind of, wading into the world of big data and algorithms
Oh, yeah.
to answer a question that might surprise some folks listening. Um, does more computing power always equal better performance?
Right.
You've sent us some really interesting research papers on this topic.
Good.
And trust me, this isn't just for like the hardcore techies out there.
Absolutely not. No, you'd be amazed by how often we kind of get caught in this idea that like bigger is better,
Mm,
without even really stopping to think like, wait, is it actually efficient?
right.
So yeah, we're going to break down some of the I think eye-opening findings about the hidden costs of
Yeah.
just like scaling up, when you're processing data.
Okay, yeah, let's unpack this a little bit. So
Yeah.
we're talking about like a new way to evaluate these systems using something called COSTI,
Hmm.
which it is catchy, right?
Yeah.
Configuration that outperforms a single thread. Basically, how much horsepower do you need before your fancy new system beats like good old-fashioned single-threaded approach?
Exactly.
I kind of love that. That's like it's like a tech showdown, right?
It is a tech showdown, and it's really interesting too because, you know, we think about for a long time the focus in big data has been how do we make things more scalable,
Oh
like
yeah.
how do we make them bigger, faster, and this research really highlights what they call like the scalability trap.
The scalability trap.
Yeah.
Okay, tell me more.
So it's this idea that we get so caught up in making something that can handle these massive data sets
Okay.
that we don't stop to think about if we've added so much complexity that a simple single-threaded approach would actually be faster.
Oh, interesting. Okay, so it's almost like a building a supersonic jet to cross the street when you could have just walked.
Exactly. Yeah, and they illustrate this with an example where they compare two systems, System A and System B. They're two versions of a data parallel algorithm.
Okay, now hold on. Pause for a sec. For those of us who don't um speak algorithm every day,
Sure.
what is that?
Yeah, so imagine you have this giant jigsaw puzzle,
Okay.
and instead of just like doing it yourself, you're like, I'm gonna split this up with all my friends, right? And so a data parallel algorithm is basically just saying, like, how can we break this problem down into a bunch of little pieces that we can do simultaneously,
Okay, got it.
so we can all work on the puzzle at the same time?
Okay, so back to our systems,
Yeah.
A and B. What makes them different?
So System A is kind of like the initial setup. It's a little more complex.
Okay.
And then System B is like we've gone back, we've streamlined, we've optimized it.
Okay.
And this is where it gets really interesting. So on paper, System A, it looks more scalable
Okay.
because as you add more cores, like more processing power, it shows these like bigger gains. But in actuality, System B, this like single-threaded version,
Yeah.
is consistently faster.
Wow, so even though it can handle more,
Yeah,
it doesn't necessarily mean that it should.
exactly. Yeah, and it just shows that sometimes just like simplifying your approach,
Right.
minimizing how much overhead you have, leads to much better performance overall,
Interesting.
even if it might not look as impressive, when you're looking at like a chart or a graph.
Right, so it's not just about brute force, it's about efficiency.
Exactly.
But what does that mean, though, like in the context of these systems? Like what are the secret ingredients that make a single thread sometimes faster?
So one of the things is how the work is divided up.
Okay.
So there are these systems like GraphLab and GraphX
Okay.
that we see a lot in this research, and they're kind of like the master chefs of data.
Okay.
Like they use these really clever strategies to chop up the data, what we call partitioning, and arrange it in a way that minimizes how much different parts of the system need to like talk to each other.
Because too much chit-chat slows everything down.
Yeah.
Too
Yeah.
many cooks in the kitchen.
Exactly. Exactly. That communication overhead can be a real killer.
Yeah.
And then the other ingredient is choosing the right algorithm.
Okay.
And so, we were talking about these scalable algorithms.
Right.
And what's kind of funny is the researchers point out that some of these algorithms are really popular not because they're the best algorithm,
Okay.
but just because they're easy to distribute across a bunch of cores,
I see.
even if that means they end up doing way more work than is actually necessary.
So it's like taking the scenic route when you could take the expressway.
Exactly.
Okay.
Yeah, and the perfect example of this is the connected components problem.
Okay.
So this is, a pretty classic problem, and the go-to algorithm for this is usually label propagation, which is very scalable.
Okay.
But the researchers showed that a different algorithm called union find could be over 10 times faster.
10 times faster.
Yeah.
For this kind of problem.
For the connectivity problems, yeah.
Okay.
And it could do that even on a single thread.
Wow. Okay, so what's so magical about Union Find? What's the trick here?
So imagine you're trying to figure out if everyone at a party is connected through friends. Right?
Yeah.
So label propagation would be like you ask each person to write their name on a piece of paper.
Okay.
And then give it to all their friends.
Okay.
And then all those friends give it to their friends. And eventually everyone has like this big stack of papers with everyone's names on it.
Lots of notes, lots of passing back and forth.
Exactly.
Okay.
But Union Find is more like asking everyone to point to one friend.
Okay.
And that friend points to another friend until eventually you kind of like trace a path back to the beginning.
Okay.
And so it's very quickly able to kind of group people into these connected clusters. And it just minimizes the overall amount of work that needs to be done.
Okay, so it's less about like that brute force and more about being strategic.
Yeah, it's about working smarter, not harder.
And this kind of brings us back to our friend cost.
Yeah.
It feels like this metric is all about exposing these inefficiencies, right?
It is, yeah. And they actually go on in the paper to show how you can use cost to analyze real-world performance data.
Oh, cool.
From published systems.
Okay.
So, for example, they looked at NIAD, which is a really cool system, but its performance on a Union Find implementation was very heavily influenced by the choice of data structure.
Okay.
They were using hash tables instead of arrays. And it turns out that one decision made a huge difference.
Wow. Okay, so I'm picturing like these big data systems are like high performance race cars.
Yeah.
Everything seems top of the line, but then you pop the hood and you realize that they put the wrong tires on.
Totally, yeah.
But why would one data structure make such a big difference?
Yeah, so think of it this way. A hash table is kind of like a library with a super fast card catalog, right?
Okay.
So you can find any book's location instantly.
Right.
But then you have to like walk all over the place to actually go get each book.
Okay.
An array is more like, having all the books lined up in order on a shelf.
Right.
It might take you a little bit longer to find the right section.
Right.
But once you're there, grabbing the next book is super quick.
I see. Yeah. Okay.
And so in something like Union Find, where you're constantly jumping between these related pieces of information,
Right.
using the array, even though it seems simpler, actually leads to much faster access times.
Right. So it's really about having the right tool for the job.
Exactly.
You wouldn't, use a sledgehammer to drive a nail, right?
Right.
But in this case, the sledgehammer is this like complex system. And then the nail is this task that might actually be better suited to a simpler approach.
And that's what I think is so cool about this cost and insight is it's like it forces us to really confront our assumptions about what makes a good system.
Yeah.
And it pushes us to be more transparent about how we're evaluating performance.
Right. So instead of just blindly chasing scalability,
Right.
Is this the right tool for the job? And if it is, how can we use it in the most efficient way possible?
Exactly. Yeah. This research isn't about saying like get rid of all your distributed systems.
Right.
It's saying like let's be a little more I guess discerning about when we choose to use them.
Okay, so like sometimes a single thread is the unsung hero, and sometimes you need the massive, cluster.
Yeah.
It all depends on the context.
Exactly.
So what are some of the, I guess, takeaways for like developers and researchers who are, working on these systems? What should they be keeping in mind as they're, building the next generation of big data tools?
That's a great question. I mean, it's like my grandma used to always say, just because you can doesn't mean you should, right?
Right.
But no, you're right. Like, if we can squeeze this much performance out of just a single thread,
yeah.
Imagine what we could do if we really put our minds to designing smarter algorithms,
right,
and using more efficient scaling strategies.
Exactly. Yeah, and actually, the author of this paper, he highlights some really great examples of high performing scalable systems that kind of like break the mold a little bit.
Oh, interesting. Okay. Any names I might recognize?
Yeah. So there's Galois and Ligra. Both of these are what are called shared memory systems.
Okay.
So think of it as like one giant whiteboard that everyone can kind of access and work on at the same time.
Okay.
And these have actually been shown to outperform their distributed counterparts when you kind of put them head to head on a single machine. And then there's also NIAD, which introduces this really interesting, what they call a general purpose data flow model.
Okay.
So think of it like as a really well orchestrated factory floor, right? Where data kind of flows smoothly from one stage of processing to the next.
Okay.
And NIAD has actually been shown to outperform even some of the more specialized systems out there.
Wow, that's really impressive. So, okay, I mean, it's inspiring to know that these like high performance systems, like they exist, but like how do we learn from them?
Right.
Like what makes them tick?
Yeah, that's the $1 million question, right?
Yeah.
It's like we need to dissect like what are the things that those systems got right? Like what design choices led to those impressive results? And how can we apply those lessons to other systems and other problem domains?
Yeah.
It's like we need to find like the hidden gems of innovation
Right.
and use those to kind of push the boundaries of what's possible.
It reminds me of that saying, good artists copy, great artists steal.
Yeah, exactly. But it's not even stealing, right? It's more like how do we adapt and evolve those successful ideas
Right.
to fit these new challenges that we're facing.
Yeah, and I think we also have to keep in mind that the world of hardware is changing so quickly too.
Oh, absolutely.
So, what works best on today's systems
Right.
might not be the optimal solution tomorrow.
It's a never-ending cycle
It is, yeah.
of innovation and adaptation.
Yeah,
But that's kind of what makes it so exciting, right?
that's true.
There's always something new to learn, something to improve.
Totally. And this paper, for all its critiques, it actually ends on I think, a really hopeful note.
Yeah.
They point out that we're actually starting to see more and more research that really critically analyzes the performance of these popular scalable systems.
Okay.
And really challenges these assumptions that we've made about how they should be designed.
So it's like we're entering like a new era of big data, one that's more grounded in reality.
Totally.
And less focused on just chasing like arbitrary metrics.
I think that's a great way to put it. And it's really about asking like the right questions.
Yes.
Right. Not just can we make this scale,
Right.
but are we scaling in a way that's truly efficient and beneficial for the problem at hand?
More cores, bigger clusters, those aren't the only answers.
Exactly.
Sometimes it really is about taking a step back and saying, okay, are we even using the right tools in the first place?
Right.
Maybe the answer isn't always about building a bigger hammer, but about choosing a more precise tool for the job.
I love that analogy. That's great.
Right.
Yeah, it's about understanding like the nuances of the problem.
Yes.
The strengths and weaknesses of different approaches.
Yeah.
And then finding like the most elegant and efficient solution. And sometimes that solution, might just surprise us. It might be simpler, more elegant, and yes, even more powerful than we could have imagined.
Food for thought, right?
It is.
If a single thread can sometimes outperform a cluster of machines,
Yeah.
just imagine what's possible when we combine these smart algorithms with truly efficient scaling.
And sometimes that solution, might just surprise us. It might be simpler, more elegant, and yes, even more powerful than we could have imagined.
It's kind of like sometimes the scrappy underdog really does come out on top, huh?
Totally. And it's funny because we talk about all this stuff.
Right.
All these like, potential downsides of scaling.
Right.
But it made me realize like I don't think I've ever actually sat down and calculated like what is the like energy cost of running some of these massive systems.
Well, that's a good point.
If we're really talking about efficiency here, like that's a whole other layer to this, right?
It's true. It's like the hidden environmental impact of our our data hungry world.
It's huge, and I don't think people are really talking about that enough.
So what can we do? Like, how do we start to kind of shift the conversation and raise awareness about this hidden cost?
Well, I think for starters, we need to start measuring it.
Right.
Right. Like if you can't measure it, you can't improve it.
Right. And we need to make those measurements like accessible and understandable.
Yes, absolutely. Like I think a lot of this stuff can feel really, really technical.
Right.
And kind of, in the weeds for people who aren't, computer scientist, but like
Right.
we need to find ways to communicate this information in a way that everyone can grasp.
Because at the end of the day, this impacts everyone.
And
It's not just a tech industry problem.
exactly. It's about the future of our planet, right?
Yeah.
Like how do we use these incredible tools that we've created in a way that's both powerful and responsible?
It's about finding that balance, right?
Yeah.
Between innovation and sustainability.
I love that. Yeah.
Well, speaking of balance,
Yeah.
I think we've reached a pretty good stopping point for today.
I think so too.
This has been a really, really fascinating deep dive.
Yeah.
Thank you so much for coming on and sharing your expertise with us.
This was so much fun. Thanks for having me.
And to all of our listeners out there, thank you for joining us.
Yeah. Thanks, everyone.
We'll see you next time for another deep dive.